Me, Bradley. Well, we lived it up in the snow. We did everything but make the snow ice cream, pretty much. I'm glad it's all gone finally. Yeah, once snow is like, you have your fun in it. Once it starts to like melt, it just gets nasty and muddy. So, and then the roads are just annoying. My car is literally like filthy right now. It needs a car wash so bad. So that's the downsides. But I would take one big snow like that every year, just one. We have friends that live up, I think I mentioned this, up in Ohio, and it's been like they've had like 12 inches of snow for like 3 weeks straight. So I don't envy them, but one good snow did my heart some good. We built an igloo. Anybody ever done a snow igloo before? It was awesome. We used to build them all the time growing up, but it was fun. It finally caved in yesterday. Okay, it's 8 o'clock, so we will get started. And a couple of announcements that I wanted to go over and remind you guys of first. The Lewis Structure Dry Lab was due last night on Mastering Chemistry. If you have questions though on Lewis structures and condensed structures, do not leave those waiting. Don't think they'll just sort themselves out in your brain. You need to take care of those before exam 2 rolls around. So please set up a Zoom meeting with me. Please reach out to me if you know other students in the class or in your lab group who seem to get it pretty well. Don't, just don't be too nervous to reach out and ask questions because Lewis structures are a big, big deal and we will use them moving forward. And I think hopefully you got my email. Hopefully everybody finished watching the lecture video from last week. That was important that you diligently watched all of that. The other thing is that the exam 1 key, like how I worked everything out, is posted. In fact, I meant to already have this pulled up, but I don't. I'm going to pull it up on Blackboard and show you. So if you go to Blackboard, then you go to the exam folder, and you should see, once you click on that folder, you should see the key. And I post keys like this because I want you to see how everything should have been worked out. I want you to have any questions you had about that. Oh, it's in a separate folder, exam keys. That's right. So it's not in the exams folder, it's in its own folder. So look right here. Here is the exam key, 1 key. And you click on that. And there it is. So I walked through some stuff I didn't necessarily explain, some multiple choice. And obviously you've had the answers for the multiple choice for a while. But I go in and I explain a few things here and there on certain multiple choice questions. A lot of people missed number 3 about and it may not have been 3 on the Blackboard exam, but it's 3 as I number it on this paper, about the octet rule. I think actually this should have been all are true. A lot of people picked all of them are true. That's a typo, actually, I'm just seeing. But it should have been that the octet rule allows us to predict whether main group elements give away or receive electrons, and then we can know what kind of charges ions will have. So if you have questions about any of those multiple choice, I add a few things here and there. I show you how you should have worked out. This was a specific heat problem right here, one of the multiple choice about that, the Arabian darkling beetle. Anyways, scroll on down. Yeah, I just add my own little notes. I show you how you should have worked out all the little prefix conversions and how you should have typed your answers in for that. The blood serum questions, okay? And note, look right here. I'm going to zoom in on this. It says these problems were pulled from Chapter 3 Mastering Chemistry homework. I got a couple emails about this problem on the homework, and I thought, that's probably a pretty good question to put on the exam then. And so sometimes I'll pull questions directly from your homeworks. Sometimes I will pull questions directly from the textbook problems that I recommend. So if you have any incentive to do really well on your homework, or ask questions on textbook problems, sometimes you'll find those problems on the exam, okay? So I changed the numbers, sure. And instead of solving for liters or something, I had you solve for grams, but literally the same style question. It was a density problem. Okay. I had a lot of people when you were doing the kind of the fill in the blanks with the table, a lot of people put decimals for the number of neutrons. Like you would put like 28.942 or 64.41. And I made a note here, you cannot put decimals. The number of neutrons in an atom must be a whole number. You can't have half a neutron, okay? And then too, a lot of people for the number of valence electrons for vanadium, they put 5. Sure, vanadium forms a +5 charge, but it's a transition metal, and all transition metals have 2 valence. Remember we said transition metals can sometimes lose electrons beyond their valence. So the number of valence electrons should have been 2, but a lot of people put 5 for vanadium. These things were pretty simple, no explanations on the physical chemical changes. I put explanations on the homogeneous and heterogeneous mixtures. I had some people mix those up. Some of people said chocolate was a heterogeneous mixture and the soup would be a homogeneous mixture. But remember, it's all about uniformity. If you have a mixture that's uniform, every portion's the same, things are evenly mixed, that's homogeneous. Heterogeneous is not evenly mixed. And then lastly, here was the conversion problem. So I just wrote down all the relationships on the side over here, and then I showed you step-by-step how I would have worked that out. A lot of people got 50.9 days, and then you rounded to 60. So I don't know if you thought it was 59 accidentally when you rounded, and I really didn't take off points, maybe half a point or something for that. But a lot of people got this problem pretty well. I would love to know, now that I've shown you this, I'm going to stop sharing my screen. I would love to know your thoughts because we actually haven't gotten to talk about the exam. What did you guys think about the exam? You know, now that you've seen kind of some of the key, and maybe you'll take some of your own time to look at that further. Which portion was the hardest? Did you feel like and logistically, was it pretty easy to take a picture and upload it as a PDF? Anybody get stuck on that or have a freak out moment with that? Any questions about the exam before we get into any lecture stuff?
I actually have a question. So
Yeah.
on that last one, it's uploading the PDF file. It wouldn't let me upload it, so I emailed it to you. Is that still okay?
Yes, absolutely.
Okay, awesome.
I tried to respond to some as I could, but usually when I get in a mode with grading, I forget to respond. So I got your emails, and
Okay.
if you obviously you can see you got points for that. And then the bonus points, I forgot to mention that if you responded to the discussion board question, I put your bonus points on that very last question. So if you got all 5 bonus points and you got the whole conversion problem correct, you should see a 15 out of 10 on that last problem. Does that make sense? If I took points off of the last problem, but you still got bonus points, then I added all that up and I put your points on that last question. Will we have opportunity for more bonus points in the future? Absolutely, Kristen. I always offer 1 bonus point opportunity, not a single bonus point, but like an opportunity to get bonus points for every exam, if that makes sense. Okay. So look for that. I have not decided just yet what it'll be for exam 2, but there will be a bonus opportunity for every exam. And usually it's about 5 points. Okay. Any other questions? How are you guys doing so far? Just have the snow days thrown you off? Do y'all feel like out of it? Do you feel like, okay, me too. So we're right there together, but we're going to jump back into chapter 4. That's why I extended the due dates for the chapter 4 homework assignment to Friday, to give you a few extra days to kind of get your feedback under you. And anyways, I'll be available. My mom actually had to have surgery on her wrist this weekend. She broke her wrist on the ice. So I have been back and forth. So if I don't answer your emails like within the same day, it's because I'm traveling back and forth to care for my mom a little bit this week. But I will respond to you guys as soon as possible because your emails are important. So without further ado, don't forget you have a quiz today, and that's open all day long. But other than that, let's jump into lecture. Okay. So we're about halfway through the chapter 4 slides. We're going to pick up with the slide that has the title Molecular Geometry. Okay. Molecular geometry. It looks just like this. Now, to remind you, the first video or the first lecture on chapter 4 covered quite a bit of content. Chapter 4 is a big chapter. There's like 6 kind of big topics in chapter 4. We talked about covalent bonds last week. And can somebody remind me, how is a covalent bond different from an ionic bond? Shared electrons. Thank you, Bailey. Okay, thank you, Molly. In ionic compounds, ionic bonds, you totally transfer an electron, okay, from one atom to another. Someone gives it away, someone totally receives it. So you have ions with positive, negative charges. In covalent compounds, we're sharing electrons, but we are still obeying the octet rule. Every atom in a covalently bonded molecule still is trying to acquire an octet. And remember, a bond represents 2 electrons, okay? And then we kind of talked about Lewis structures towards the end, a lot about Lewis structures and condensed structures. And I want to go back to this slide for just a second, because I think it's so important that this can be a key for you guys to remember how different atoms should look within a Lewis structure. That carbon should always have 4 bonds. And here's the different ways that carbon can look over here on the left. To remind you which atoms can be central atoms and which ones are only perimeter atoms and can never be central or part of the main chain. You'll hear me say that phrase main chain a lot when we're talking about condensed structures, okay? The rules for Lewis structures, some practice problems. If you want to have questions on any of these, I actually did number 4, but if you wanted to try number 6 or number 5 there, and you have questions, you can let me know. So anyways, and then we ended with condensed structures. Here was some stuff. I was working some with a student yesterday. So these are not easy. Condensed structures are not easy. These are going to be one of the hardest things on exam 2. Okay. So again, please practice. You're going to get more comfortable with them the more you practice. But do not be frustrated because a lot of it is trial and error sometimes. Okay. You realize what you did wrong and you got to try it again. That's just how you learn some of these things. So let's start with molecular geometry. So to intro this topic, why is this important? Well, Lewis structures, we said, are important because they help us see how the atoms are connected. And that gets really, really important, especially further in health sciences when you're talking about chemical reactions in the body and why pain medications work. Pain medications are often just a blocker for different nerve responses, okay? They just kind of deaden your nerves, they block nerves, and it matters what things bind to what and how it blocks what different things in your body. And so molecular geometry is important too, because we live in a 3-dimensional world, not a 2-dimensional world. Lewis structures are just a 2-dimensional representation of atoms and molecules and bonds, but geometry is a 3-dimensional thing. Things take up space, okay? And that's important too. So Lewis structures help us keep track of valence electrons and the geometry. Or the shape of the molecule, okay? Electron location determines the geometry or the shape, all right? So again, you see that electrons are really the fundamental basis for everything in chemistry, including this. So when we're talking about geometry or shape, maybe some of you had geometry in school. It's all about the shapes of things and how atoms are gonna orient themselves, not just how they're going. And here's somebody make sure you're on mute. I'm getting some background noise from somebody. Just everybody double check that you're on mute really quick. And please remember that I ask all of you to have your video on with us this morning if you're going to join us. Thank you guys. Please turn your video on if you can. So we see several different shapes here, okay? Depending on how many atoms are involved in the molecule, 3, 4, 5, 6, everything's going to have a different shape, okay? And it also depends if you have lone pairs. That's going to have a different shape. So as you're looking at these things, methane CH4, you see it has this kind of shape right here. The carbon atom is right here in the middle, and then you have those 4 hydrogens oriented around it at equal distances. Ammonia, NH3, looks a little bit different. Water, this is a molecule of water, and it has this kind of bent shape. And then you have stuff that's linear as well, straight line, and we'll talk about all of this. Now, what you can see, what's visible when you look at the geometry are 2 things. The atoms are obviously visible and the bonds, okay? You see these sticks right here that are connecting. Yeah, if your camera isn't working, that's okay, but if it is, please join us. The bonds, you see these sticks right here? That's called a bond. So we can see the bonds and we can see the atoms. But what we cannot see, but what is still important for the geometry, are the lone pairs. Okay. Electrons. We can't see those. You should recognize when you look at ammonia, for example, that nitrogen has a lone pair. So the blue one right here, this is nitrogen, and it should have a lone pair on it. And sometimes what you'll see people do is they'll kind of draw a little cloud around it, like a little lobe around it. to show this is where the lone pair would be. We don't see those when we actually just look at the geometry. Oxygen as well. This is oxygen in the water molecule. Oxygen should have 2 lone pairs on it. Okay, and so you would probably see a picture with 2 different lobes around it. But we don't see those when we actually name the geometry, but they are important for determining what the geometry is. Okay. Now, all of this is based on something that we call the VSEPR model. And what does VSEPR stand for? It stands for valence, shell, electron, pair, repulsion. Okay, so if we break this down word by word, valence shell, obviously that's the electrons in the outer shell. Electron pair repulsion. So electrons we know are negatively charged. And because of that, when electrons are close to one another, they repulse each other. Okay, the negative charge repels, opposites attract, same like charges repel. And that's what forces the geometry. That's what tells different atoms where to go and how far apart to be. Okay. So it all, again, has to do with the electrons. So the electrons in the bonds and lone pairs repel each other. They get as far apart as possible. And that's what forces the geometry. Okay. So that's what the VSEPR model stands for. So know what that stands for in case I were to ask you. All right. So
Hey,
how do we...
can you go back up again?
Oh, yes, I
I'm
can.
sorry.
Thank you. No problem. So in just a second, we're going to learn there's 3 rules, kind of like for Lewis structure that we had 5 rules. And in just a second, we're going to see there's 3 rules for how we determine geometry. And then we're going to practice a lot with geometry and we'll do some poll questions. You good, Glenn?
Yes.
Okay. All right, so rule number 1, how do we determine the geometry? How do we determine a molecule shape? Well, number 1, you're going to draw the Lewis structure. And then you need to figure out, okay, which atom am I trying to name the geometry for? We are not naming the geometry of every single atom in the molecule. We are only naming the atom. Usually it's the central atom that we want to name the geometry for. Okay, so we are not naming the geometry for the perimeter atoms, just the central atoms. So I'll come right back, but let me scroll back up. So for example, if we're looking at ammonia here, we're not naming the geometry for all these hydrogen atoms. This would be hydrogen, hydrogen, hydrogen. We're not naming those. We are trying to name the nitrogen, okay? We're trying to name the geometry just for the nitrogen. That's our central atom, okay? So you have to consider which atom is central, which one's my center atom, and you're going to usually name the geometry of that. Sometimes a molecule can have more than one central atom, and we'll get to that later. But just remember that's step 1. Number 2, find the number of, okay, I'm going to introduce a new phrase here, charge clouds. Charge clouds. What the heck is a charge cloud? Okay. Find the number of charge clouds on the central atom. So a charge cloud, I'm going to tell you how you count charge clouds. Essentially, what are charge clouds? These 2 bullet points tell you how to count them. Bonds are charge clouds. Okay. Bonds including double and triple bonds count as 1 charge cloud. Okay. So if I have a single bond that's connecting atom X to atom Y, that's a charge cloud. If I have a double bond connecting atom X to atom Y, we still count that as, it's 2 bonds, I know, but you count it as 1 charge cloud. Or if I have a triple bond connecting atom X to atom Y, that is still counts. I know it's 3 bonds, so you're going to be tempted to say 3 charge clouds, but it's all just 1 each, 1 charge cloud each, okay? Lone pairs also each count as 1 charge cloud, okay? So bonds and lone pairs, that's how you count charge clouds. So you're going to find your central atom, and then you're going to say how many charge clouds are on my central atom. Next, number 3, you're going to predict the shape, okay? So charge clouds will move as far away from each other as possible, and this requires you to visualize the molecule in 3D. So the table right down here is going to help you predict the shape. Everybody good with this slide right here? Okay, I'm going to scroll down.
Hold on. I was
Okay.
my mic was muted. No, I'm sorry.
You're good. It's all right. All right, so those are our 3 rules. This table that I'm about to show you is going to put these 3 rules kind of into, well, it's kind of a summary table, and then we're going to practice putting the 3 rules into play. All right, I'm going to scroll on down. Okay, so this table, it's in your notes, so you will have access to it. I would have it printed and readily available, handy right there on exam day. Don't have to go digging for this. This is kind of a rubric or a key of sorts for geometry. So if you have this available and it's got all the different names, so you don't have to, I'm not asking you to sit and memorize all this, okay? Back when we were face-to-face and my exams were not open book, open note, yeah, people had to memorize all this. So consider yourselves fortunate, but you can use this on the exam. So let's read this table. But first, I'm going to make one edit to the table, and that's this first column right here on the far left. Instead of number of bonds, I want you to mark this out, and instead I want it to say number of bonded atoms. Okay, I know that's a subtle change, but here's why that's important. You're going to be tempted to just count the number of bonds, and you're going to be tempted to count a triple bond as different than a single bond. But when you are counting charge clouds, remember, you have to count them the same. So instead, you're going to say how many different atoms are bonded to my central atom. Okay, so that's why I want to name this column number of bonded atoms, not number of bonds. So the next column says number of lone pairs. So as you can see, we're trying to calculate the total number of charge clouds. So if you count 2 bonded atoms and no lone pairs in your structure, that's a total of 2. You just add up those 2 columns. The number of bonds plus the number of lone pairs, that equals the total number of charge clouds. Once you figure that out, if you have 2 charge clouds, your molecule, the geometry there is linear. Okay, that's a linear molecule. It's a straight line. All right, so for an example, carbon dioxide over here, the way it's oriented, you see how you have 2 double bonds. So if you counted individual bonds, you would count 4 here, and that would automatically count you wrong. You wouldn't get 2 charge clouds. But if you count the number of bonded atoms, we have 1 oxygen bonded here to the carbon. We have 2 second oxygen bonded here, so 2 bonded atoms. We have no lone pairs on the carbon. Okay, let me differentiate something. You do have lone pairs on those oxygens. You are not counting lone pairs on the exterior perimeter atoms. You are only counting the lone pairs on your central atom, the one you're trying to name the geometry for. On carbon, you never have lone pairs. So that's why we're saying 2 bonded atoms, no lone pairs, so total 2 charge clouds, and we get a linear geometry. Okay? Yes, you do have lone pairs all over these oxygens, but I'm not concerned with naming the geometry of my exterior atoms. I'm trying to name the central atom. Okay? So you're viewing this all from the viewpoint of the central atom. Okay, if you have 3 bonded atoms and no lone pairs, that's a total of 3 charge clouds. You would call that a molecule like that, trigonal planar. Everybody say it with me, trigonal planar. I'm serious, 1, 2, 3, trigonal planar. Everybody wants to say it trigonal and all kinds of stuff. It's trigonal planar, okay? So an example here would be a carbon with 2 hydrogens and an oxygen attached. And I'll show you in a minute why we call that, kind of why the triangle part is part of the name there. We'll view it from the top down and it will look like a triangle. So trigonal planar, all those atoms are in the same plane. All right, so on and so forth. You can see how if you have 2 bonded atoms, 1 lone pair, that adds up to 3 charge clouds. We call a molecule like that bent. All right, and you're given different examples over here on the far right of different molecules that have that geometry with real atoms. And then down here, if we move on to the next set of brackets, if you have 4 bonded atoms, no lone pairs, that is 4 charge clouds. So any of these scenarios are 4 charge clouds, right? Any of these scenarios up here were just 3 charge clouds. So there's 3 different ways things can add up to 4 charge clouds, depending on how many bonded atoms and how many lone pairs you have. And each of them have a different name: tetrahedral, pyramidal, or bent. So we're about to break this down step by step. All right. So I'll come back to this table, but for now, this is just kind of an overview. I want to look at each one of these in depth, okay? So let's look at linear first. So if you have 2 charge clouds total, because you have 2 bonds, or 2 bonded atoms, and no lone pairs, we said that was linear. And the example here, a different example, CO2 or HCN, okay? The reason it's linear is because your exterior atoms, obviously carbon is the central atom here. but your exterior atoms, and this first one, hydrogen and nitrogen, they're oriented 180 degrees apart from each other. So no matter how you rotate or look at this molecule, it's a straight line. It's linear, okay? Another example with different kinds of bonds would be, again, the carbon dioxide molecule. And just a reminder again, yes, there are lone pairs in the molecule, but none of those lone pairs are on the central atom. So that's why we're saying 2 bonded atoms, no lone pairs, okay? Questions on how something is linear. You do not have to memorize the bond angles here, the fact that it's 180 degrees apart, but that does help you recognize, oh yeah, that's going to be a straight line. All right, let's move on to 3 charge clouds. If I have 3 bonded atoms and no lone pairs, we said that is trigonal planar. Trigonal planar. So here, like I said, is a top view. Okay, so it's the same molecule from the table up above, the carbon with the 2 hydrogens and an oxygen. And yes, there are lone pairs on this oxygen, but we say there's no lone pairs on the central atom is the one we're concerned with. So if we're viewing this from the top down, you can see how it forms a triangle, okay? All of these atoms are roughly, it's not exact, but roughly 120 degrees apart. We know a full circle is 360 degrees, right? So each of these are about roughly 120 degrees apart. And that's why we say it's a trigonal planar, and all these atoms are in the same plane. If you held like a piece of paper flat, they would all be in the plane of the paper, okay? A side view down below. The dashes and the wedges, so like right here, oh, about dropped my pencil. Obviously, this is a dash line. Anything that's dash indicates that it's behind, like it's sticking out behind, and the wedge indicates that that atom is coming towards you, forward from the plane of the carbon, okay? But that's from a side view. From the top view or from the bottom view, they're all in the same plane. But if you view it from the side, then the carbon and the oxygen would be in the same plane, but that one hydrogen would be sticking backwards and one towards you, okay? Questions on that? Trigonal planar, okay. Another way you can, things add up to 3 charge clouds, but a different geometry, is if you have 2 bonded atoms, 1 lone pair, we say that is bent, okay, that is bent. So an example here is a sulfur with 2 oxygen atoms. And obviously some of you are like, okay, I'm seeing something that looks really interesting right here. Why does this oxygen have 3 lone pairs and only 1 bond? This breaks all the rules. There's something we have not talked about that you will talk about in further chemistry classes if you were to take an kind of a higher level one. It's called resonance. Don't worry about it for here. Sometimes electrons can move around within a structure. Like sometimes these electrons can decide, oh, I'll make a second bond here. And these electrons can say, oh, I want to jump on this oxygen as another lone pair. And things can just move around and shift. And so you get resonance. Don't worry about it. I know it looks bizarre and not what I taught you guys, but you just learn things can bend and break the rules the further you dive into chemistry. But we do have 2 bonded atoms, and we do have 1 lone pair on our sulfur. Okay, that's what we're concerned with. We're not counting the lone pairs anyways on our exterior atoms. Okay, and remember when you view the geometry, we said what's visible is the bonds and the atoms. What's not visible is the lone pairs. So that's why when we look at the molecule over here, we don't see the lone pairs. We're just visualizing the bonds and the atoms. And this is a bent structure. It's a bent shape, okay? So anytime you have this scenario up here, 2 bonded atoms and a lone pair, you have 3 charge clouds, that molecule would be bent. Can anybody think of another molecule that would be bent? We're actually going to get to another one. It's got a different number of charge clouds though. I'll come back to that question. Okay. So the bond angle here, roughly these oxygens are about 120 degrees apart. That's because one thing I wanted to explain, this lone pair right here. Lone pairs are very kind of, they're kind of bossy, and they tell the other atoms where to go. So they need their own space. Anybody, you know anybody, they just need their own space. Anybody, you're kind of more of an introvert and you just need your own space sometimes. That's kind of how lone pairs are. And so they are literally pushing these oxygens around. They're pushing these oxygens closer together. All right. Let's keep going. 4 charge clouds. 4 bonded atoms. Sorry, I did not edit these slides. I should in future. And no lone pairs. That one was, anybody remember the name for this? It's probably on the slide if you're looking at the whole slide.
Tetra something. Tetrahedral.
Tetrahedral. This is a very geometry oriented word, okay, tetrahedral. That is because an actual tetrahedron in the world of geometry is a shape with 4 sides to it. So if you're looking at, this looks like a pyramid, right? Do not confuse this. This is not a pyramidal. That's another geometry we'll look at in a second. But if you're looking at this triangle shaded red here, we do have 4 sides, a bottom side and then 3 triangular sides on top. And the center atom here is our carbon with these 4 hydrogens. So you can see how the tetrahedron is fitted to this molecule, okay, with all the hydrogens at the exterior points of the tetrahedron and that carbon in the very middle. So these 4 bonded atoms, anytime you have an atom in the middle with 4 things bonded to it, it's going to be a tetrahedral, okay? Carbon, we know carbon has to have 4 bonds, and so often you see it with 4 single bonds, right, in Lewis structures. So guess what? Very frequently, not always, but very frequently, carbon is a tetrahedral. Earlier we saw it in the molecule CO2, it was linear, but very often it's a tetrahedral, okay? The bond angle here is even smaller. So again, the more atoms you add bonded to your central atom, the smaller the bond angle is, the less space they have to orient themselves apart from each other. Okay, another way you can have 4 charge clouds would be 3 bonded atoms, 1 lone pair. We said that's going to be pyramidal. Pyramidal. Okay, again, don't confuse this with the fact that I said the word pyramid up here. I was just looking at the shape for this tetrahedron. Okay, pyramidal. Ammonia is the classic molecule to represent pyramidal geometry, because nitrogen, anything that can form 3 bonds and has a lone pair, not anything in main group 5, so nitrogen, phosphorus, a lot of your main group 5 elements will tend to be pyramidal. Not always, because you could have a double bond and not just 3 single bonds, and that would change the shape as well. But if it's 3 single bonds and a lone pair, that is pyramidal all day long, okay? Again, I'm not going to ask you to memorize all the slight variations of the bond angles, but again, you can see here how bossy the electron pair or the lone pair is. The electron lone pair is literally pushing all these hydrogens down towards each other. Okay, they're kind of the boss and they take up the most room. So lone pairs tend to do that. And again, when you visualize the shape, you see how it's a pyramid like that. Okay, we don't visualize the actual lone pair. We don't see the electrons when we draw the actual shape, but they do play a role in determining what the shape is. Questions so far on geometry? Am I moving too fast? Y'all good? It's okay.
Yeah, kind of moving too fast a little bit.
Moving
I'm
too
kind of
fast?
confused.
Any questions? Do I need to repeat anything or go over anything?
So I guess, do you have to have a specific set of bonds for it to be, I guess like I don't know what like the answers are, like pyramidal or whatever. You know?
You don't, Glenn, that's a great question. You don't necessarily have to have a specific kind of bond. Like, we're not telling you anything about whether they're single, double, or triple bonds here. Okay, so that's a great question. It's not necessarily the kinds of bonds. What matters is the number of atoms that's bonded to your central atom. Okay,
Mhm.
so here the central atom is the nitrogen. Okay, I'm going to erase because I've scribbled all over this now. That's not the eraser. Okay, if we're looking at this molecule, nitrogen is our central atom. Now, yes, in this example, we have 3 single bonds, but that's not what's important. What's important is that I have 1, 2, 3 hydrogens bonded to that central atom. And what's also important is that I have 1 lone pair that I can label here. That is what matters in determining the geometry.
Okay.
It is literally 1,000 degrees in this office. And so, I'm sorry, everyone. So that's what matters. Does that help, Glenn?
Yeah.
We're going to work some examples with like drawing out and naming the geometry in a minute. And I think it'll click some more, but that's a great question. It does not matter the kinds of bonds. What matter is the number of atoms that is connected to your central atom. Okay?
Yeah. So like, I have another one.
Yeah.
Right quick, is that sort of that said 4 bonds and 1 a lone pair? Would it still be the same answer?
4 bonds and 1 lone pair?
Yeah.
We
Weird.
actually don't have a scenario like that. So at least in this course. So we actually, if we have 4 bonds, we have one with no lone pairs. That's up here. But we actually don't have a scenario where we're running into 4 bonded atoms and a lone pair.
Okay.
That would put you past an octet. That would
Okay.
put you at 10 if you counted the electrons there, because every bond counts for 2 electrons. Then a lone pair would be 2 more. That would put you at 10 electrons past an octet. Now, sometimes you have atoms that can do weird things and exceed octets. Okay, there are exceptions, but we're really not focusing on those or getting into that here. I'm just introducing the basics.
Okay.
Yep, great question though. Okay, the last way you can have 4 charged clouds: 2 bonded atoms and 2 lone pairs. And we say this also is bent. So notice there are 2 ways that you can add things up to get a bent molecule. All right. 3 bonds in a lone pair, or I think it was two bonded atoms in a lone pair. We looked at an example with SO2, and then 2 bonded atoms and 2 lone pairs is also bent. Water, a water molecule, is a perfect example here. And you see how we have 2 lone pairs, 1, 2 on our central atom, which is oxygen. And these are pushing those hydrogens really close together. This is the smallest bond angle we've seen yet, 104.5. And then when you visualize the actual geometry, notice we don't draw the lone pairs in, we just draw it with the bonds and the atoms over here. The oxygen in the red and the hydrogens are the spheres in the white right here. Okay, so as a review, all the ways that things can add up to 4 charge clouds and the different geometries, tetrahedral, pyramidal, or bent, are covered right here in this slide. Okay, so this is just a review slide, so I'm not going to sit here and read everything because this is literally, we just talked the last 3 slides over these 3 things. Okay. All right, so now we're going to put this into practice after one last thing, and then we're going to put it into practice. I mentioned this earlier, but I'm coming back to this. Sometimes you can have a molecule that has more than one central atom, and we call this multiple centers. Multiple centers. That is a molecule where you have more than one central atom. Okay. So in this case, each atom that is a central atom can have a unique geometry. You can name the geometry, and they may be different for each central atom. Let's look at an example. Here we have this molecule. We have a carbon with 3 hydrogens, and we have a carbon with 1 hydrogen and an oxygen. So both of these carbons right here, that one and that one, these are both central atoms. And we can name the geometry for each of these carbons. So I want to look at the carbon on the left, okay? I'm going to highlight this carbon in yellow. Okay, this one. Let's name the geometry. That obviously you see it pointed out next to you, but how did they come up with tetrahedral? They said that this carbon on this is just kind of a ball and stick model. You see the picture on the right. So this carbon number 1 right here is the same carbon we're talking about, number 1 right here. How did we come up? They said it's tetrahedral. How did they get that? Well, to be tetrahedral, you have to have 4 bonded atoms, no lone pairs. So how many atoms are bonded to this carbon on the left? We have 1
4.
hydrogen. Yes, thank you. 2 hydrogens, 3 hydrogens, and a carbon. That's the 4th bonded atom, is that other carbon. So we have no lone pairs. So because there's 4 bonded atoms, no lone pairs, that's why we said it's tetrahedral. The carbon on the left, I'm going to highlight it in red. They said that one was trigonal planar. How did they come up with trigonal planar? We have 1, 2, 3 bonded atoms. An oxygen, a hydrogen, and another carbon are bonded to that carbon, and we have no lone pairs. So that is why they said it was trigonal planar. Okay. So now that you know that you have some molecules where you have multiple centers, you can name each of them uniquely, individually. Let's do some practice. Okay. So here's the review slide for the rules. So you can refer back to this if you need to. But I'm going to scroll on. We literally went in, we filled in the blanks on all this earlier. So I just copied and pasted that slide so that we have it close by. Now we're going to do some examples, okay? So the first thing you need to do, rule number 1 on all of these, is draw the Lewis structure. And then let's identify what atom are we going to name. So for C3H8O, we're going to draw the Lewis structure, and then we're going to look at which atom are we going to try to identify the geometry for. So there's probably multiple ways you could draw this and get a correct structure. I'm going to put all my carbons in a row. All right, 3 carbons. And anybody have an idea of what I should do next?
3 hydrogens on the first carbon, 3 hydrogens on the last carbon, and 2 on the middle.
Okay, if I do that, the only thing I run into, Kristen, is the fact that I now no longer have a
Oh,
space
your
on
oxygen. Yeah, okay.
So that's.
Could you connect an oxygen to a carbon and then put the hydrogens off the oxygen?
That's great, Bailey. Any of these hydrogens, it does not matter which one. I'm just erasing the one on the end. You can put a hydrogen there, or an oxygen there instead, and then you can throw that hydrogen on the end. You could literally have erased any of those hydrogens and drawn in the oxygen and reattach the hydrogen like I just did. Okay. Now, how many central atoms here do we have that we can name? Four. Okay. Which 4?
The carbons and the oxygen.
Carbons and the oxygen. Good. We can name the geometry for every single one of these carbons. That one, and that one. We can also name the geometry of the oxygen. It's central here because it has more than one thing bonded to it. Okay. So let's look at the first carbon on the far left. This carbon right here. What's the geometry for that? Anybody?
Tetrahedral.
Okay, tetrahedral. How did you come up with that, Kristen?
There are 4 bonds, and carbon doesn't have any lone pairs, so it's 4 and 0.
Okay, so we got 4 bonded atoms. I'm just gonna mark them off in green. 1 hydrogen, 2, 3, and a carbon. Those are the 4 bonded atoms that are bonded to this carbon, okay? No lone pairs. So if you go look at your key from earlier, that table that I told you to always keep handy, way back here. 4 bonded atoms, no lone pairs, that is tetrahedral. Good job. Scroll back down. So tetrahedral for there. And then guess what? I'm going to go ahead and look at the second and the third carbon as well. Okay. So if we're looking at this carbon, I've got 4 bonded atoms on it as well. 1, this carbon would be the second bonded atom, 2, 3, and the third carbon is actually the 4th bonded atom for this very center carbon. 4 bonded atoms, no lone pairs. That's tetrahedral as well. And guess what? The last carbon looks the same. 4 bonded atoms, no lone pairs. So I'm just going to draw a blanket tetrahedral, and all those arrows indicate. If you get a lot of carbons that are tetrahedral, you can just draw many arrows to the same spot and write it one time.
Wait, so how do you know like if something has a 0 like lone pairs or 1? I'm still kind of confused on that.
If it has lone pairs like this drawn on it or not. So like none of these carbons have any lone pairs directly on the atom. This oxygen here, you see, this is 1 lone pair, and these 2 dots down here represent another lone pair. So that would be 2 lone pairs on your oxygen. But these carbons, okay, I'm gonna color that in black again. These 3 black carbons, none of these have any lone pairs. They only have bonds, only dashes or lines coming off of them. Does that make sense, Glenn?
Yeah, it makes sense.
Okay. So now if we go to the oxygen, we're gonna name it. I've got a blue line drawn here. How do you guys want to name this one? Any guesses?
Bent.
Okay, how did y'all come up with that?
2 bonds and 2 lone pairs.
2 bonded atoms. Let's label those. 1 carbon and 1 hydrogen. That's 2 bonded atoms. And then we already numbered off the lone pairs in red. So that makes it bent. Okay, it adds up to 2 bonded atoms plus 2 lone pairs equals 4 charge clouds. And if you go to the key and look, That is bent. Okay, I could have done that math for everything else as well. The carbons over here, all of them were 4 bonded atoms and 0 lone pairs. Okay, so that all added up to 4 charge clouds. Sorry, I'm abbreviating so much. So always add up, count your charge clouds. Remember that was after you draw the Lewis structure. So we did that. Then we worked on finding the charge clouds. And then we looked at our table to predict the shape. Okay, so you just follow these through step by step, and that is how you label everything. All right, let's do, I want to pick a more challenging one. Let's do 5 right here. You guys go ahead and draw the Lewis structure for that. And then I want you, to the best of your ability, identify your central atom. There should just be one in this case, and label the geometry. Okay.
Okay, like,
Oh, go ahead, Glenn.
like, I'm just gonna take a guess. So, like, would it just be a hydrogen dash carbon dash nitrogen?
Like that.
Yeah. Would it
Okay,
just,
so then you got to ask yourself, does your carbon have 4 bonds? How many bonds does a nitrogen need? Do we have any lone pairs? I think you've oriented the atoms the right way, but we got to make sure everybody has an octet.
oh. So like nitrogen, that needs 5 bonds, right? Or 3.
In chat, Molly said a triple bond. I like that. Nitrogen should have 3 bonds. And it should also have one thing we're missing now.
1 lone pair.
One lone pair completes the octet on nitrogen. Okay. All right, so we have one central atom here, and it's carbon. And how, anybody want to tell me how you should name it?
Linear.
Okay, I'm seeing different things, bent, linear. Okay, so let's count the charge clouds. We have 2 bonded atoms, a hydrogen and nitrogen, and we have no lone pairs on carbon. So that is 2 plus 0 equals 2 charge clouds. Oops, C, 2 charge clouds. How do you find the elements so quickly on the periodic table? Well, for me particular, Bailey, I've been doing it for a long time. But I actually don't even have a periodic table around. That would probably be handy. I think down here. Oh, there's one. So there's the carbon and the hydrogen. Are you talking about for drawing the Lewis structure, Bailey? And the nitrogen.
Yeah, like I feel like everyone so quickly
Have
finds
this
them. I'm like,
out. Keep this sheet out.
Yeah, is that
What
sheet,
I did, Bailey.
that key?
Yeah.
Maybe just have
is
that
that the
available.
one from the beginning?
That's
of
the one
this?
from the video lecture last week.
Okay.
Yeah. So 2 charge clouds, and remember that one is linear. Okay, so we'll name this carbon linear. All right, so that's geometry. Okay, now I know we have different people. If I ask you right now, how do you feel about geometry? Some people would be like, great, good, I'm ready to go on. Some people would be like, I need to do all of that over again. Okay, and that's okay. We have to accept the fact that this class has a wide audience of people, and that's okay. We're all in it together. So if you are one of those people that you feel great about it, good. But if you're one of those people that are like, oh my gosh, I don't get this at all, please know that I'm not trying to just blow through this stuff, but we have a lot of other topics we do have to cover today. So I'm not putting this down and saying goodbye to it. Please reach out to me. I have an office hour that starts at 9:30, and I would love to go over these things more with you. All right, but this is all the time that I can allot to spend right now on, I think I might actually have a poll question on geometry. So let's do a little review. I'm gonna launch this poll question, geometry. Okay, so right here on the sheet, in CL3, the poll question says the geometry of nitrogen in NCl3 is what? So I want you to take a minute, try this one on your own as well. We're gonna answer this poll question, then we got to move on to polar bonds. All right, we're about a minute in. I'm gonna give you about 20 more seconds, and then we're gonna call it and look at it. I'm gonna go ahead and start drawing the Lewis structure out so we can look at it. You should have a nitrogen. We got
Just
3
guess.
chlorines. All right, go ahead and get your answer in. Nitrogen should have a lone pair. All right, in the poll and share the results. Okay, so most people, 63% of you guys said pyramidal, but we had all the other choices picked as well. So why is it pyramidal? Okay, so you need to count. We've drawn the Lewis structure. That was step number 1. Now we're going to find the number of charge clouds, step number 2. Remember, we're going to count bonds, including double and triple bonds, as 1 charge cloud, and you're going to count lone pairs, all count as 1 charge cloud. So let's go count those. In red, I'm going to count 1, 2, 3 bonded atoms. We got 3 chlorines there. Okay, so we're going to do 3 bonded atoms plus I can count 1 lone pair on that nitrogen. So 3 plus 1 is a total of 4, I don't want to do that, charge clouds. 4 charge clouds. So 3, this was bonded atoms. And 1, this should be lone pair. 1 lone pair. So when you go look at the table from earlier, up here, 3 bonded atoms, 1 lone pair, 4 charge clouds, that adds up to pyramidal. Okay, that's why I think this table is so handy to have. So that's how you do that one. So the correct answer there was pyramidal. And if you picked any of the others and you're just confused as to why it's not that, please drop by my office hours, shoot me an email, and come talk to me more about geometry. I'm happy to help. Okay, let's move on to polar bonds. So we're going to put a pin in geometry and Lewis structure for right now, and we're going to talk about polarity. Okay, so I have 2 pictures here. At the top, we've got 2 hydrogen atoms bonded to each other on the left. In the green over here, we've got 2 chlorine atoms bonded to each other. And both of these are identical atoms, right? 2 identical atoms bonded to each other in a molecule. These are both diatomics. Remember, by the way, do not forget what atoms are diatomics. That was important from the video lecture. And I want to ask you, what is the difference between the 2 molecules up top and this molecule on the left? Obviously, this one is like rainbow colored. What's the main difference, though? The main difference is that we don't have 2 identical atoms. Hold on, I have a question in the chat. Is our quiz over both chapter 4 lectures or just the previous one? Just that first one from last week. Yeah, none of this stuff from today will be on the quiz because it's so fresh. Okay, so we've got 2 identical atoms bonded in these molecules up here, and then these are 2 different atoms bonded together. We got hydrogen and chlorine. And when you have 2 different atoms bonded together in a covalent bond, they're sharing electrons, you have the potential and the opportunity for a polar bond, okay? That is because we know that certain atoms like electrons more than others. Okay, we've looked at ionization energy, we've looked at electron affinity. You should know those terms from chapter 3. We know that certain atoms like to gain an electron. They attract electrons a lot more than other atoms. Some atoms are happy to give up an electron. Here, if you had to look between hydrogen and chlorine, which one do you think likes to have electrons more? Hydrogen or chlorine? Which one has a higher affinity for electrons?
So I see here.
Chlorine does, okay? Chlorine has a higher affinity for electrons. You could call it an electron hog, okay? An electron hog. It wants to hog the electrons towards itself. Another phrase that I'm going to introduce for this is called electronegativity. Electronegativity is very, very similar to the idea of electron affinity, okay? Someone's electronegativity just means that if you have a high electronegativity, you like electrons, okay? So if we were looking at this as a tug of war match, because remember, there's 2 electrons in this bond right here, and both of these atoms are pulling on the electrons. Why are both atoms pulling on the electrons? Well, both have a nucleus, and the nucleus of every atom is positively charged, remember? So every atom is attracted to electrons based on the positivity of its nucleus. But it's just that chlorine has 17 protons, 17 plus charges in its nucleus, okay? Hydrogen has 1 proton, 1 plus charge in its nucleus. So if you think of this as a tug of war match, it's 17 people on one side and 1 person on the other. So obviously, which one's going to win? The chlorine, okay? So because the electrons are going to be pulled towards, I should do this in red, that would make more sense. The electrons are going to be pulled towards the chlorine. Chlorine's going to win the tug of war match. We can draw in these partial negative and the partial positive signs that you see right here. It's a lowercase Greek letter for delta. So you can call it a squiggle or we just call it a partial positive and a partial negative, because the electrons are actually pulled more towards chlorine than they are towards hydrogen. So because there's higher electron density around chlorine, we say the chlorine is it's not ions here, but it's a partial negative and a partial positive, kind of like ions, just not all the way. Okay, they're still sharing, but they're not sharing evenly. Okay, the electrons are shared unevenly. And this is how you get polar bonds. Okay. Up top, these electrons are shared evenly. Why can we say that? Because it's identical atoms on both sides of that bond. The tug of war match is perfectly even.
So anytime the atoms are different, it's always going to be polar.
Not always, but the potential for it to be polar is there.
Oh,
we're going to look at a table that gives us a little more information, Kristen, but you're headed in the right direction. You're thinking along the right lines. Okay, so I had a periodic table here. I really want to get down to this one. Okay, when we're talking about electronegativity, that phrase I talked about earlier, you can assign every atom on the periodic table, and in fact, they've already done it, an electronegativity value. And if you notice, which atom on the periodic table has the highest? This is an electronegativity chart. It's pulled directly from your textbook. Which atom on here? Fluorine. Fluorine has the highest, right here, fluorine. Got a value of 4, has the highest electronegativity. So therefore, any atom that is fluorine or close to it, they're gonna hog electrons towards themselves. So usually when those are in a bond, unless it's 2 fluorine atoms, then that's a nonpolar bond. Okay, but if it's like hydrogen and fluorine, guess what? Those are usually going to be polar bonds, because you're going to have a very uneven sharing of the electrons. Okay. All right. So now, how do we determine if a bond is polar? It's not just the fact that you have 2 different atoms in the bond. You have to calculate electronegativity difference. So we're going to be using that electronegativity chart a lot. Electronegativity difference is how we measure how polar a bond is. We have different levels of polarity, if that makes sense. So how do you calculate electronegativity difference? Here's 2 examples. Okay, you got carbon and nitrogen in this first bond, and you got carbon and oxygen. So I've already told you the electronegativity values down here. Okay, 3, if you go look at the electronegativity chart above, nitrogen has an electronegativity value of 3, carbon is 2.5. So we're going to pull those values down here, and they've already done it. You're going to subtract the lowest number from the highest number. You should always get a positive value. Subtract the lowest number from the highest. So this is the value for carbon. That was the value for nitrogen. We're going to subtract those, and you see a difference of 0.5. All right. The one with the lower electronegativity value, that one's going to be the partial positive. The one with the higher electronegativity value will always be assigned the partial negative if it's a polar bond. Same idea over here. You've got carbon and oxygen this time. Okay, the 3.5, this is the value for oxygen. The 2.5 is the electronegativity value for carbon. You subtract those and you find the difference. The electronegativity values come straight from this table, and you'll have this table provided for you on the exam. But this is also in your textbook or here on your slides. So you'll need to have access to this table, Molly. We're just looking at those numbers. You can see carbon was the 3.5. All right, so when we subtract those, we get a difference of 1. So this is even more polar bond. The larger the difference is, that comes down to these blanks down here. The larger or the bigger the electronegativity difference, the more polar the bond is. So which bond is more polar, a carbon-nitrogen bond or a carbon-oxygen bond?
Carbon, oxygen.
Carbon-oxygen bond. Okay, this one is, well, it says it for you, more polar. Okay. Questions on bond polarity. Here
What
is
did you say
actual,
about the larger and the smaller, or about the partial positive and partial negative on those, or how
I'll
do we
say,
determine
yes. So the element that has the lower electronegativity value, here it's carbon. In both of these cases, it had the lower value. We always assign it with a partial positive if it's a polar bond. And the partial negative will go on the atom that has the higher electronegativity. Okay. Now, sometimes you can get an electronegativity difference that's very, very, very small, like 0.1 or 0.2 of a difference. We actually don't, even though the electronegativity values are different, we actually don't classify it as polar until the bond difference is 0.5 and above. I'm going to say that again. Sometimes you can have 2 atoms in a bond and their electronegativity values are different, but we do not classify a bond as polar until the difference in their electronegativity values is 0.5 or above. In fact, the actual range is 0.5 to 1.9. If the electronegativity difference falls between 0.5 to 1.9, like when you do the little subtraction problem up here, if your answer falls 0.5 to 1.9, we call that a polar covalent bond. That bond is covalent. They're sharing electrons, but it's polar. They're not shared. The electrons are shared unequally or unevenly. A covalent bond, you'll also hear me say this is non-polar. Okay, the electrons are still shared pretty evenly. Okay. So covalent, I call it nonpolar or polar bonds versus covalent or polar covalent. Just your textbook uses covalent and polar covalent. So again, if the difference is 0 to 0.4, that's nonpolar. If it's 0.5 to 1.9, that's polar. And if it's 2.0 and above, we just go ahead and call that ionic. The electron has totally jumped ship. You have ions now. Okay. So something that's ionic is so polar that it is just ionic. Okay. Questions on this? I think I had a poll question. So here you can look at CF, a bond of CF, NaCl, and rubidium with fluorine. And you can see their electronegativity differences. 1.5, they've already calculated it for you. 1.5, 2.1, and 3.2. These are the difference values. So you can look at where they fall on the table. Let me erase so you can read. And you could classify these as polar, nonpolar, or ionic. So if we're looking at carbon bonded to fluorine, the difference is 1.5, it falls here. So we would call this bond polar. Sodium chlorine and rubidium with fluorine. Those differences are so large that we just call these ionic. Okay, that falls down here in this category. So guess what? The electronegativity chart right up here. This thing is going to be really handy, really important for a lot of chapter 4 homework problems on Mastering Chemistry. And this table right here. Use these two tables, use these two resources as you work your homework problems. Okay, I have another poll question. Let me launch this really quick. Okay, I want to know here, I'm going to leave this electronegativity chart here for you. Which of the following is a polar bond? So you got carbon bonded to carbon, nitrogen bonded to hydrogen, carbon bonded to hydrogen, and sodium bonded to chlorine. Which one? Only one of them is polar. So you need to find the electronegativity difference using the chart for each of those bonds, and then see from that table on the slide above if it's polar or non-polar. Anything that's 0.5 to 1.9 difference is polar.
I accidentally like submitted mine, and I think I got it wrong. So,
That's okay. I can't see names. I just see numbers.
uh,
And this is not for a grade, right? All right, I'm going to go ahead and call it and show the results. We are only 61% voted. Okay, get your votes in. Another 10 seconds. 10, 9. Go ahead and vote. Almost there. Once we hit 90%, I'm going to call it. Come on, get your votes in. All right, if you got a guess, just do it. We're going to go over the answer. All right, I'm going to end the poll. So the most commonly picked answer, 75% of you guys, almost, selected the nitrogen-hydrogen bond. So let's look at this. Number one, when you have two identical atoms bonded together, you don't even have to calculate it. You know the difference is 0. So that carbon-to-carbon bond, the first choice, it's not going to be polar because those electrons are shared perfectly evenly between the two nuclei in the carbon atoms. There's the same number of protons in a carbon nucleus. So therefore, those electrons are shared perfectly even. Okay, because 2.5, this is the electronegativity value for carbon, minus 2.5 is 0. That's the carbon-to-carbon bond. Okay, nitrogen to hydrogen. So the value there is 3.0 and 2.1. So we're going to do 3.0 minus 2.1. Those are the electronegativity values, and you get a difference of 0.9. And guess what? Looking at this table, that falls right between these numbers, 0.5 to 1.9. So this one is polar. So that should have been your answer, and you don't even have to do any more. But I do want to make the point here. Carbon to hydrogen, let's look at that one really quick, because you're going to see tons and tons and tons of carbon-hydrogen bonds. What are the values there? 2.5 and 2.1, looking at the periodic table. So 2.5 minus 2.1 is a difference of 0.4. This is almost polar, right? It's almost polar, but it's not. It falls right here. It's a difference of 0.4. So you should always classify carbon-hydrogen bonds as non-polar. You're going to see so many of them. Please know that a carbon-hydrogen bond is never polar, okay? That's why I put that one on there. And then sodium and chlorine, that's ionic. So different, it's ionic. Okay, we're running out of time, and that's not good because I had more stuff to cover. I am going to hit polar molecules in the last remaining minutes of our lecture today, and then we will have to, I'm going to make a video on naming binary compounds. It's only like 2 or 3 slides down here. I will make a video and I will post that today. It'll be, I promise, 12 minutes or less. And please watch that because you'll need it for your chapter 4 homework. And then on Thursday, we're going to pick up with chapter 5. Okay. All right. So polar molecules. So not only can you have a single individual bond that is polar, you know, molecules are the sum of all the atoms and all the bonds in the molecule, okay? So you can have entire molecules that are polar based on three things. There's three determining factors. Number one, do you have any polar bonds? Okay, if you have polar bonds in your molecule, good chance you're going to have a molecule overall that is polar. Okay, number two, do you have any lone pairs? Okay, this is all about how electrons are distributed in the molecule. Okay, this is all about how electrons are distributed. So if you have lone pairs, that's obviously where the electrons are, and that's going to be an uneven distribution of electrons. So that's going to contribute to your molecule being polar. And then you have to consider the shape. Okay, if you have symmetry, if you have 1 and 2, but your molecule is symmetrical, chances are your molecule is not polar. We're going to look at an example of that. Okay, so symmetry matters. If your shape is not symmetrical, you could probably have a polar molecule. So you got to consider the shape. So let's look at a molecule of water. Remember the partial negative and partial positive signs, that squiggle minus and the squiggle plus, okay? We got oxygen and hydrogen. If you were to calculate, we're not going to do it right now, but if you were to calculate the electronegativity difference for these particular bonds, I want to know, do you think that those are polar bonds or no? If you just had to guess, oxygen and hydrogen. When you do the electronegativity difference, you're going to see these are polar bonds. Okay, the difference between oxygen. So what that means is oxygen is hogging the electrons more. It has a higher electronegativity value if you go look at the chart. So these electrons in this bond, they are pulled towards the oxygen, okay? Oxygen is hogging those electrons. So we can write a partial positive on the hydrogen, and you see that is done for you. But even beyond that, oxygen has 2 lone pairs. So it's really electron dense. Does that make sense? Oxygen's so electron dense. It's pulling the electrons in the bond towards itself, and it has lone pairs. So that is why we're going to put partial negatives on this end of the molecule. If we had to literally just divide the molecule up, one end and another end, we have an end that is electron rich, and we have an end that is electron poor. The hydrogens are the end that is electron poor. And when that happens for a molecule, you can draw this arrow right here. You see this arrow with the little cross on the other end? We call that a dipole. You can draw a dipole in. It's an arrow with a little plus on the other end. It makes it look like a plus sign down on this end, right? And we orient that on the region that is partial positive, and we draw the arrow towards the region that is the partial negative. It's kind of like an overall big picture thing, all right? Let's look at another example. Chloromethane, CH3Cl. Cl is next to fluorine. And remember, fluorine is the most electronegative atom on the periodic table. So guess what? And chlorine has all these lone pairs on it that they have not drawn in. So it is really, really electronegative. Remember, carbon-hydrogen bonds, none of these bonds, not polar. Okay? They're not polar, but what is polar is this bond right here. This one is polar if you calculate the electronegativity difference. And again, we're not taking the time to do that just yet because I'm kind of crunched on time. But now that you know how to do it, if you went and did it, you would see these polars, or these bonds down here, carbon-hydrogen, not polar, carbon-chlorine bond is polar. And chlorine has all those lone pairs on it. So we draw in the partial negative sign there, and you could put partial positives on all these hydrogens. So if we draw the dipole in, overall, it should be pointing towards the chlorine, and you put the plus sign on the partial positive region of the molecule. Okay, so we're saying this top half of the molecule is really electron dense, and this lower half of the molecule is really electron poor. Okay, does that make sense? Now, the last thing we've not talked about is shape, symmetry. So a perfect example is carbon dioxide. So carbon-oxygen bonds, that's the only kind of bonds we have in this molecule, is a carbon-oxygen bond. If you calculate the electronegativity difference, and we did this earlier, you get a difference of 1. Okay, so it is 3.5, that's the value for oxygen, minus 2.5, that's the value for carbon. You get a difference of 1. Okay, and again, I happen to know these numbers from the table. You could easily go look at the table and calculate this in a heartbeat yourself. This is polar. Okay, so these bonds right here are polar. Because of that, we say, okay, the carbon is the less electronegative, so it gets the partial positive. The oxygens are the partial negative because they're more electronegative and they have lone pairs. We got polar bonds and lone pairs. This has polarity written all over it. Until you recognize the fact that this molecule, if you draw the dipole in, how are you going to draw the dipole? That's my next question. You want to draw it pointing towards the electron. You got to draw two of them. And when that happens, you see that they cancel each other out. When you draw them in the exact same directions, but they're opposite, you can draw a plane of symmetry right here in the middle. Both halves of this is the same now, okay? So when your molecule is symmetrical and you have dipoles drawn in opposite directions, they cancel each other out, and this means zero net polarity overall. That molecule is nonpolar, even though, yes, it has polar bonds, and even though, yes, it has lone pairs. Okay, so up here, we did not have symmetry. We could draw one directional dipole overall, and it didn't cancel out. But down here, when you can draw two dipoles and they cancel each other out, then you have symmetry, your molecule's net polarity overall, zero net polarity overall. Same idea if you're looking at carbon with 4 chlorines, and I literally am on the last minute, so I'm going to wrap it up. But if you draw the dipoles in, it gets even crazier here. You draw dipoles pointing towards all these chlorines. You got one left, one right, one up, one down. You got 4. That's a lot, but they all cancel. The left and the right cancel. The up and the down cancels. So symmetry ruins your polarity. No polarity. Okay. All right. I had a poll question I was going to do, but we're at time right now. I know your brains are so fried. I know this is a lot. Chapter 4 is kind of a beast of a chapter. So if you have questions, I'll stick around, or join me on my office hour at 9:30. If not, don't forget your quiz for today, and I will see you guys on Thursday. I'm going to post a video about naming down here on Blackboard later today, this evening. Have a good one, guys. Any questions? Riley, is the quiz over last week's stuff? Yeah. So Lewis structures, covalent bonds, how electrons are shared, how do you satisfy the octet rule there, those kinds of things. Condensed structures. Yep. Kristen, did not really understand the symmetry except for the first one you did an example of. Okay, you want to hit that again really quick, Kristen? All right. So if you have, we'll just erase and look at the second one. If I were to draw, you see the geometry for this, if you draw the formula, it is CCl4. Okay, CCl4, that's the formula for this molecule.
Mm-hmm.
And if we draw the Lewis structure for this, it's probably easier to understand. I'm going to draw the Lewis structure of it. Need some space right here. C, and I'm going to draw 4 chlorines. And then you got all these lone pairs on all the chlorines, right?
Mm-hmm.
Okay, so once you get that drawn, you have something that looks like this. Now, if you're trying to assess, is this molecule polar or not? I want you to go through the 3 things we mentioned earlier. Does it have polar bonds? Do I have lone pairs? Is there symmetry? So first and foremost, do we have polar bonds? Well, how do we calculate if bond? What kind of bond do we have in this molecule? We only have one kind. You see 4 bonds, but all those bonds are identical when you look at it.
Mm-hmm.
So what kind of bond do we have? It's a single bond between what atoms?
Carbon is a central atom with chlorine.
Yep, you have 4 carbon-chlorine bonds. Okay, you got 4 carbon-chlorine bonds.
Okay.
They're all identical, a carbon-chlorine bond. That's the only kind
Right.
of bond you have. So we
Right.
need to say, is this bond, since we only have one kind of bond, is that bond polar or non-polar? How do we figure that out?
Look on the chart for their electronegativity.
That's correct. So carbon, I can go ahead and
Carbon
tell you, is what?
2.5.
Okay. Oh, you can't see my screen. I've been drawing this whole time.
No,
Oh,
it's 0.5. The difference is 0.5, so it is polar. Because chlorine's
Okay.
3.
this is what I've been drawing, by the way.
Yeah, I had it, but okay, so it is polar because the difference is 0.5.
That's right. So when you do 3.0 minus 2.5, you get 0.5. So this is polar. Every single bond is polar. So what I want you to do is go in and draw your partial negative and your partial positives. We're going to put one partial positive. What atom should we put that on?
The central atom, carbon.
Right there. Boom. Positive. Okay. Now let's draw the partial negatives in.
Okay. Mm-hmm.
And you're going to put a partial negative on all these chlorines.
Mm-hmm.
So now I want you to draw your dipoles in, because we draw a dipole oriented from the partial positive towards the partial negative.
Okay, so just 4 arrows going out to
Then-
each.
One left, one right, one up. I don't care if you draw over your atoms, it doesn't matter.
Okay.
And one down.
Okay. Mm-hmm.
So you've got lone pairs, you've got polar bonds, but then when you look at the shape, and the Lewis structure helps you here,
Mm-hmm.
I think the Lewis structure is easier than looking at the
Yeah.
geometry structure up here.
Yeah, I didn't really understand looking at it that way, but it makes more sense this way.
Where did my drawing go? Oh, here it is. So now notice that the one on the right and the one on the left, they cancel.
Yeah.
Run opposite ways. The one on the top, boom, and the one bottom cancels.
So it's the dipoles that make the difference?
When you draw a dipole, if you have a permanent dipole, one that does not cancel, that's a polar molecule. So
Okay.
the molecules we had up here were water and chloromethane.
Mm-hmm.
We threw a dipole in and it doesn't cancel with anything.
Right.
Some people would be tempted to say, oh, water has a plane of symmetry right here. Both sides are the same. But does your dipole cancel with anything?
No.
No.
Okay. Yeah, it makes more sense with the drawing the Lewis structures.
Yes. Yes. Okay.
Okay.
Well, good deal.
Okay.
I might include a minute or two of this stuff on the video as well. And
Yeah.
I'll do a practice problem on the video, but I really need to get to naming so you'll know how to name these compounds.
Mm-hmm.
And anyways, all that'll be on the video. And yeah. Any
Okay,
other
cool.
questions?
Mm-mm. All right. Thank you.
Okay, thanks, Kristen.
Mm-hmm.
Any other questions, guys?